Good morning. Thanks everyone for joining us. The first of a two-part webinar series we are presenting this fall on the effective use of F280-12 for determining a home's heat loss and gain. Today's webinar will focus on how to collect the data required to complete an F280-12, and next month's webinar on November 20th will center on interpreting the output report to select an optimally sized heat pump. And my colleague Amanda Brewer is going to share the link to that next webinar if you'd like to sign up for that as well. Next slide, please. I'd like to take this opportunity to highlight Indigenous leadership in the space of high performance building, low carbon, climate resilience. So Seychelles Nation, they purchased and salvaged, relocated, and repurposed many homes in the Lower Mainland that were slated for demolition. Seychelles is located in the Sunshine Coast of BC between Jervis Inlet and Howe Sound. So in 2023, they took 59 homes in Port Moody on the Lower Mainland and that were part of a demolition project. They were in the inlet district of the redevelopment project. The Seychelles Nation acquired 10 of these homes that were identified by the company as suitable for rescue, relocation, and repurposing. In 2024, the homes were relocated by truck and barge to Shelt, where they underwent energy efficiency upgrades and renovation to create two-story intergenerational homes within the nation's Selma Park subdivision project. And where possible, the upgrades were completed using existing cabinetry and appliances from the 49 homes that could not be salvaged. Through the leadership and collaboration of Seychelles Nation, Renewable Developments, and West Group Properties, this project saw multiple co-benefits, helping to address the nation's housing crisis, support Indigenous families and elders, reduce costs, limit waste and embodied carbon, and reduce the need for new materials. So just a little inspiration and innovation for this morning. Next slide, please. So I work for Community Energy Association, and since 2017, we've been delivering training on high performance building approaches and technology. This work supports local governments and Indigenous communities looking to develop capacity in local industry. BC local governments know that businesses in their communities need access to training to meet the growing demand for high performance homes, and that's where we're coming in. We're a registered charity and nonprofit that accelerates bold action by local governments and Indigenous communities on climate and energy issues. And I'm very pleased to introduce our instructor for today is Rob Pope. We get to work with Rob often, in-person workshops, consulting on our Retrofit Assist program, and many webinars like this. It's always very really great technical knowledge and a good presenter. Rob, could you please take it away?
Thanks, Ketan, and thank all of you for taking the time to attend this. I hope I'll make it worth your while. This is the practical application of F280-12, and what we're doing in this session is kind of highlighting the more critical inputs that are required to make an effective and accurate load calculation, set of load calculations. And that's kind of based on what typically goes wrong, where the errors typically occur. And we'll point out the impact of those as we go. As far as the structure of this session, here it is. The introduction is what is F280 and why we need it. The importance of actually using verified, CSA verified F280-12 software tools. And we're going to talk about the two approaches to load calculations, block loads and room by room loads and how they're applied. We're going to go from there to the meat of the session, which is the inputs and how they impact the design. or the load calculations. So the design conditions, for example, the location, the outdoor indoor temperatures, homeowner expectations, the geometry and orientation of the building, guidance on accurate interpretation of plans. We're going to talk about building assembly details, R values and U values, infiltration, and so on. And we're going to try and demonstrate how impactful it might be if some of those inputs are done incorrectly or inaccurately using a very recent case study. We'll go through that case study. And as was mentioned, there's going to be some polling questions along the way related to the subject matter. So it's not a test, so don't worry about it. But, whatever you think the answer is, just try your best, and we're not evaluating anybody on this. Okay, and at the end, we'll have questions and discussions, but if it's relevant to what we're talking about in a moment, I don't mind interrupting the presentation to have a discussion. I kind of like doing that. Okay, so here we go. First slide is a poll. Why do we need load calculations? 1, it's required by code. 2, it's required to determine the capacity of heating and cooling equipment. 3, it guides the design of heating and cooling systems. Or is it all of the above?
All right, we're good. 93% of you have said all of the above.
Wow, you guys are really good. That's correct. Of course, yeah, you need it for all those reasons. It's required by code. It's required to determine the capacity you need for heating and cooling, creating comfort really in the home. And it's absolutely necessary to guide the design of the heating and cooling systems. It's a CSA, Canadian Standards Association standard, and that's the standard that governs the methodology of doing heat load calculations for residential buildings. It's embedded in the code, section 9.33.5. And using this standard, among the other things that we just talked about, is going to ensure comfort. It's going to reduce installed HVAC system costs. And the reason that is because otherwise, 90% of the time, I mean, there's exceptions, but the majority of the time, overwhelming majority of the time, systems are far oversized. It also ensures you comply with code, and it reduces your risk of liability because, there's nothing worse than having an unhappy homeowner that causes you time and money to address something that could have been done accurately in the first place. So you want to reduce that liability as well. So there's 2 approaches. A block load. So block load is the whole house. It calculates the heat loss and gain of the entire house as one single space. Despite how many rooms there are, it just takes the shell of the building and the total heat loss and heat gain of that building. It's used for energy modeling and is almost exclusively used for retrofits on existing homes. A room by room load, on the other hand, is required for new construction. You just can't do a block load and use it for new construction. And it's the only approach that can adequately inform the HVAC system design. You can't design a mechanical system without knowing where the loads are in each of the rooms. How much does the bedroom need? How much does the bathroom need? And so on, for cooling, for heating. So the block load, more for existing homes, not exclusively, and room by room exclusively for new construction. So we're going to spend a bit of time on existing homes and then move on to new construction. So doing a load calculations for existing homes is not easy because you got to find out what's in the walls. The windows don't still have the labels on them and so on. The assessment from an HVAC contractor requires a lot of work. Got to measure everything up because there's rarely plans. but probably the majority of retrofits, at least in BC, is probably going to have an energy advisor. And the energy evaluation is going to be useful, not just to the homeowner for grants and incentives and so on, also for the information it provides on how to upgrade the building and potentially the cost benefits and all that kind of stuff. It informs the homeowner quite a bit, but it also informs the HVAC contractor. So the energy evaluation, which will have a HOT 2000 um, um, set of calculations performed, can be used to collect the data, the inputs, what the windows are and the infiltration is and all that kind of stuff. Or it can be used to convert to a CSA F280 approved load calculation. So for example, homeowners, they might be thinking about not just their mechanical system, their heating system, but windows and window upgrades, insulation upgrades, maybe some sealing to make it a little more airtight. That's where the energy advisor comes in. The energy advisor will do an inner guide for existing homes evaluation. That's what it's called. At the end on the right there, you'll see that's kind of a snapshot of what it looks like. There's obviously a lot more to it than that. And for the HVAC contractor, its benefit is it gives the HVAC contractor a better understanding of the existing home performance and gives the contractor the opportunity to utilize the data to support a heat loss calculation and heat gain. I'll show you what I mean in a second here. So you take the HOT 2000, which is what the energy advisor is using, and you can do one of two things. You can take that information, just raw, and you input that information, you just marry it to a program called Volta Snap, which is CSA approved. It's a verified software. And that will give you the CSA F280-12 output, the load calculation, because you have to keep in mind HOT 2000 is not CSA approved as a load calculation. It is an energy modeling program. It is not a set of load calculations. And the other way you can do it is, instead of using that program, Volta, to convert it, you just take the information that the energy advisor has gathered for the house, all the input details, all the assembly details, as you can see here. And then you just simply input them into your preferred software program for load calculations. And those programs might include, well, we're going to talk about room by room going forward, but let's just talk briefly about what's approved. There was a time when there was a lot of load calculation programs out there claiming to be CSA F280-12. But if you took an identical house with identical inputs and used all these various programs, they would be all over the place. They didn't agree with each other. The variance between them was quite substantial. So government with CSA got a bunch of people together, and we took a house that we know what the loads were on this house. This was a test house in Ottawa, and we measured all the programs, these different softwares against that known entity to see what the variances were and where the variances were. So we'd see one program was way too high, another one a lot lower, and so on. And we'd go into the programs and find out why. Then we went to all the software providers, like, for example, Tekka, RightSoft, HeatCat, VoltaSnap, and others, and gave them the information, and then requested that they update their software so that it aligns more accurately with our baseline, with our test house. And they did. It was a long process, took a lot of back and forthing, and but now we have programs that we're, very comfortable with. They agree with each other if everything else is the same to within a very small margin of variance. And these programs are TECA, which is the kind of go-to program for mechanical contractors in BC. RightSoft, a little more sophisticated TECA, and it is one of the preferred programs for not just doing the load calculations, but designing the system. HeatCAD, similar to RightSoft. And then VoltaSnap that we talked about before, which converts a Hot 2000 modeling set of calculations to an approved, verified CSA F280-12 set of load calculations as an output. And there's a link down here to HVAC DC. HVAC DC, by the way, is HVAC Designers of Canada. And they are the entity that guided this process, along with many others. We're going to be using RightSoft in this presentation. And we're going to be using it for this. So this is an example house. This is an actual house that was built that we worked on, and was built way up in the north of Vanderhoof from a builder that we know well, Northern Homecraft, very good builders. The house designer in this case was Latitude 48 Design Limited. It's a 2-story, single detached, just over 2,000 square foot house. Now that 2,000 square foot, just over 2,000 square foot, is to the exterior face of the walls. And it's an important thing to note, and we'll see why later in the presentation. But as you can imagine, to make the house look bigger, I guess, or whatever, for maybe selling purposes, whatever, you go to the exterior walls and the house looks a little bigger, but the actual living space is what we're concerned with. It's the rooms that you're in. It's the inside walls that we're doing the calculations for. You can see this is in climate zone 7A, way up there, cold. And this house was going for BC step code 5. So anybody want to guess the heating load? I'll give you another quick glimpse. That's the house. Call it 2,000 square feet. Vanderhoof, very cold, climate zone 7A, step code 5. What do you think the heating load is going to be? So we're going to the poll again. Okay, so about 45% said 35 and change. Option number 2, 18. Option number 1, 18% that is. 35% said 19. Option number 3. And a few said option number 4. Interesting. This is why we need to do load calculations, because we don't want to guess. The actual answer is number 2. That's the heating load. And you can see there the cooling load is 16,175 BTUs. So as you can see, guessing the load is not a good idea. Never has been, caused a lot of problems. So, okay, so we have a project and we're going to start the load calculations. We've got the right program, and we have a set of plans. What are we looking for first? Floor plans. Well, what do we expect from the floor plans? We're going to need the grid lines, because we need to have spatial proximities and all that kind of stuff, right? So we need grid lines. We need scale. What is it? 1/4 inch per foot, 8 inch per foot, 16th, whatever it is. We need scale. We need the orientation, north, south, east, west, or something in between. We need that. We need the rooms labeled. We can't be talking about room 1, 2, 3, 4. Or rooms that have no label. It's just a room. We need to know what that room's function is, right? A bedroom is a lot different than a kitchen when it comes to load calculations and so on. And we want to see where the windows and doors are, and skylights, by the way, with their sizing. So that's from the floor plans. If you don't have any of those things, get them. Ask for them. Don't proceed without them. Say this, and I'm working on the load calculations. I need this. I need that. You're going to want to have section plans as well, because what we get from the section plans are the elevation heights. So I mean, it gives you a different perspective of the building. That's one thing that's really important, but it also gives you elevation heights so you can see what the ceiling heights are and so on in each of the rooms. The above grade, below grade orientation of it. Ceiling roof details comes from the section plans. Vertical window placements, is it you know, a two-story set of windows, you know, on an open to above floor, for example. Exterior overhangs, they're very important. We'll see why later on. And of course, again, labeled rooms. So we say we got the plans, we have everything we need on the plans. We're going to start the load calculations. This is what we're going to put in. We're going to put the design conditions. The design conditions, again, that's the outdoor winter, outdoor summer, indoor winter, indoor summer condition that we are trying to achieve. The geometry of the building, of course, above grade walls, foundation walls, exposed ceilings and floors, exposed headers, shadings, infiltration, ventilation, internal gains, that's occupant loads. Now, we're not going to go into them all, but we're going into the ones that come up quite often as uh, problem areas in load calculations. So inputs for load calculations, design conditions. It's pretty straightforward. We have to design to some conditions. So we design to an extreme of some sort. And so we're establishing an outdoor condition in the summer. So it's, you know, the hottest days, the 2.5%, and the winter coldest days, not the absolute coldest, but a percentage. And we are designing an indoor temperature. While it's that hot outside, what temperature do we want inside? That is our design condition. That's how that everything pivots on those numbers. And we get the information we need from a number of sources, but the code source is table C2 in the BCBC, the BC Building Code. As you can imagine, they don't have the design climatic design conditions for every town, every city in the province. So what you have to do is go to the nearest one. In this case, for Vanderhoof, there's no Vanderhoof in this table in the code. So it's Prince George. So the design conditions, the outdoor design conditions, winter is minus 26 Fahrenheit, minus 36 Celsius. Pretty cold. It's really cold. I've been there in those conditions. In the summer, it's 82.4 Fahrenheit or 28 Celsius. Now, here's the thing. The nearest location to use for your design condition is not always accurate. It's a good idea to check. And if you do a check, and this is very available information on Environment Canada site, look at Vanderhoof. How many times have we gone over that 28 degrees? Starting in 2021, then 22, 23, 24. I actually went back to 2020. That's when we had the heat dome, but there wasn't enough room on here to do it, and it didn't matter anyways. The point is still the same. We exceeded, look how many times we exceeded that design condition. So the question then becomes, well, what are we going to design for? The code? Remember, the code is a minimum, right? We have room to customize that number. And if you look at this, you may want to do that. You know, the design condition um, during the summer is quite a bit different than it is in the code. The other thing, and I can't emphasize this enough, one of the common issues that comes up is you've designed the house and you've done the load calculations correctly, everything's right, and the installation is done, people move in, and you get the call in the summer, it's not cold enough, it's not cool enough. Well, it's hitting your 74 degrees, which is the, sort of the standard. It's actually 75, but 74 is a common one, isn't it? Yeah, but I want it 72 or I want it 70. Ah, okay. That's a whole different thing. My point is this. It is important to make sure that the indoor design temperatures, both for winter and summer, are aligned with the homeowner's expectations. That, whatever they're expecting, that's what you design to within reason. If they said, I want my master bedroom to be 68 or, 20 Celsius in the summer. Well, that's not reasonable. That's kind of below the threshold of what this kind of refrigerant can do. You need a wine cooler or something like that to do that. It's not reasonable. It can be done, but you're kind of outside of the limits of the threshold of reasonability there. So managing the client's expectations is not just about um, protecting them from themselves, making them understand what is realistic and what isn't, but it's also a way to inform yourself about what to design for. So let's say we did that, and instead of like we keep the outdoor condition for winter the same because frankly it doesn't have much effect, much difference. The indoor winter temperature, however, does. Maybe they want it 72 degrees or 22.2 Celsius instead of 70, which is the standard approach. The outdoor summer, as we saw in the actual data from Environment Canada, was much higher than the BC code minimum. And so let's bump that up, create some resilience in the system for changing climate. It's getting warmer. And we bump it up to 32.7, 91 degrees. And we change that indoor temperature setting. Now the thermostat's not set for 74, it's set for 72, which is almost always the case. Homeowners want it to get down to 72. Maybe they don't have it at 72 all the time, but at least it's capable of getting there. What difference does that make? We customize the design to the output of the load calculations.
Rob,
Yeah,
we have a question from Edwin Guerra. Would you ever consider using design temperatures from ASHRAE, like HTTPS,
no,
ASHRAE, Meteo instead, and which might have closer locations to your project site?
no, no. We want to. ASHRAE is a standard for Part 3, for one thing. It's a very heavy-handed for Part 9. So we use it for a lot of standards, but not for design conditions. We already have the design conditions embedded in the code. Those are the minimums we have to use. And we also have extremely easy access to the actual design conditions. Like looking up what the last 5 years were uh, for Vanderhoof, for example, probably took me 10 minutes, 15 minutes. It's nothing, right? Very easy. That's the real information that you want to use. And additionally, it's the indoor temperature too. You can guess, you can use a standard, and that's the ASHRAE standard, by the way, 75 winter and whatever that is in Celsius, and 70 um, in 75 summer, 70 in winter. I'm sorry, I don't know what the Celsius conversions are off the top of my head for that. But yeah, you're probably going to get complaints. It makes a big difference if you're in an institution, if you're in an office building, or you're in a mall, or you're, you know, in a factory setting, in a part three setting, practically of any kind, the majority of them, and it's average. The average temperature will make some people a little uncomfortably cold and some other people a little uncomfortably warm. On balance, it's okay. That's kind of the idea. But in a home, we don't have that luxury. We have to be a lot more precise.
Okay.
So how much difference do you think it'll make? Let's just go back one slide. So what did we do? We changed the indoor winter design condition. We changed the outdoor summer design condition and the indoor summer design condition for that house. So 20%, 10%, 5%, what do you think?
Okay, so about a third say it's a 20% increase, almost half say it's a 10% increase, and 22% say 5% increase.
Interesting. Very interesting. So here's the actual increase. 5%. 5% in this case here. I mean, it could be more than that. Depends on the size of the building and the complexity of it and all that kind of stuff. But in this case here, the modest size home in a very cold climate, it only had a 5% increase. In fact, it's less than 5%. And what is the implication of that? So you can see by changing and customizing to reflect the reality of the condition in the location where the house is being built, to reflect the desires and expectations of the homeowner, to build in a little climate resilience. The load went to 36,386 from 35,525, and it increased not even close to 1,000 BTUs on the cooling load. It was a 2.4% increase on heating, 5.5 increase on cooling. So we can see here what we're demonstrating here is that to do these things, it really has a marginal impact on the load, right? It has a marginal impact on the ducting, the design, the total cost and budget, the choice of equipment, very little impact on the implementation of the system compared to satisfying the comfort of the homeowner with all the other stuff that comes with it, resilience and expectations being met and that kind of stuff. It's my point here is it's a value that's worthy of consideration. Customizing it has very little impact for the value it potentially can give to the project. Okay, so that's about design conditions. We'll move on to geometry in case, unless anybody has a question about the design conditions.
I think you've really answered it, Rob, but Barb was just asking, what do you do when a customer wants their home cooler in the summer? Personally, and I know others like a cooler home winter and summer. And this looks like the customization option.
Exactly. Yeah. Yeah. Um, that's what we're doing. Our whole job is not to put in mechanical systems. It's to provide comfort. It's to provide a comfortable, healthy indoor environment. That's our job, really, at the end of the day. This is what we're talking about here. This is all the stuff behind the curtain to achieve that goal. So in our sample house, now this is a pretty simple geometry. This house, it's just a rectangle, 2 stories directly aligned on top of each other. But what if it wasn't? What if the upper level overhung the lower level? Now, this is a screenshot from the actual program rights off of the floor layout. And what you're seeing here is the second floor. So I'm going to show you now the lower floor. You can see it's different color. The upper floor is green, the lower floor is brown. And what I did is I extended the upper floor to create an overhang. And the reason I did this is because, I mean, there's all kinds of overhangs, and some of them are really small and discreet, but they make a difference. In this case here, we have, therefore, exposed floor in a small portion of each of these rooms on the south-facing side of the home. It's these areas here. Right? Is it that big of a deal if you miss it? Well, let's see. So you can see this is a 3D screenshot from the same program, right? Soft. You can see where the overhang is here. Without the overhang, we know what the loads are. If you remember, 35,525 for heating, 16,175 for cooling. And look what happens. If we put that little extra couple of feet of overhang on that upper level, create a little bit of exposed floor in each of these rooms, we end up with a 38,000 BTU load instead of 35. So there's a 3,000 and change difference. 17,000, it goes up a little bit in the cooling. Yeah, we see this quite a bit in staggered levels in houses typically occur when there are dormers, very often, front door overhangs, split level homes, and many different kinds of architectural styles. The impact on the project, however, because this is answering the question, does it really make a big difference or not? Well, yeah, it does. In this case here, just putting that little extra bit, don't forget it's not that much when you look at one room, right? Each room, there's a little bit of overhang that you might have missed. But if you missed it, this is what's going to happen. You've gone from a 3-ton unit to a 3.5 or 4-ton unit. So now you've increased this, you've gone past the threshold of the size delineations. So, there's more money for that. There's a bigger unit, bigger ducting, and so forth that you might have missed. So let's talk about orientation. One of the things I want to say first, like this house is really well designed actually, because look at those overhangs. This is the south-facing view that we're looking at, and we have massive overhangs. And what does that do? That shades the glazing, right? So we don't have direct solar gain coming into the house. There's a massive impact, and we'll see how much of an impact that is in a later slide. For now, let's just say we get the orientation wrong. This is south facing. That's the north facing view. And let's just switch them around. If we change this view to the north view, we gain 36, we go to 36,000. So we gain almost 1,000 BTUs on the heating load. And the cooling load is only slightly affected. There's about an 800, give or take, difference in the cooling load. So it does have an impact. And now, oh yeah, imagine if there were no overhangs here, right, in the south view. Now this south view would have had a cooling load substantially higher. And we'll see that later. It wouldn't be 16, it would be higher. And then we turn it around and suddenly it goes down. And what would happen if we got the orientation wrong in that situation is we'll have an undersized cooling capacity for the house in our load calculations. So we'll move on to building assemblies. That's your U and R values of each of the components of the building. And that's including the solar heat gain coefficient of glass and the rate of infiltration through the envelope. Okay, and you can see like each of the CSA approved programs will have a summary sheet where all the assembly details are put in there. and they usually have some sort of illustration of like a pie chart, of what's having the most impact on the building, which is useful.
Rob,
Hmm.
we have a question. We've gone a little past this part, but it's still fresh in our minds. Tommy asks, based on that heat calculation with the customized design temperature, would the contractor decide to choose a 3.5-ton heat pump or round down to a 3-ton?
Wow. Okay. What was that? It was a little while ago. Uh, that's this one, right?
Mm-hmm.
Well, that's, another reason. This is what coordination is all about. If it were me, I would probably, I would say, okay, here's the situation. Technically, we're just a few hundred BTUs over the 3-ton unit. I think we can get away with a 3-ton unit. What that might mean is that we put in a little more auxiliary, or auxiliary we didn't have it. Maybe you got a fireplace. Maybe you just, expect there's going to be a few days where you're going to put a sweater and some slippers on. What do you think? And then the homeowner will answer that question, and you can go from there, right? So if they can understand what the upside and downside of their options are, then they get to make the decision. And you put that decision for your own benefit on the record, right? As long as they're well informed, and that's part of your job. So personally, if the load is that close to a 3-ton unit, I'd probably stay at the 3-ton unit. I wouldn't go over.
Rob, do you want to comment on maybe like the benefit there also of like variable versus conventional equipment too,
Yeah. Well, if
in
you're,
terms of suction?
yeah, I personally, here's the thing, there's not all heat pumps are created equal. Of course, it's like anything, right? And starting at the lowest end of the tiers of performance, you have your single speed heat pump. It's on or off. It's full capacity, no capacity, full capacity, no capacity. I put my first one of those in the 1970s. Thank goodness we've moved on from that, but they still exist in the market. If somebody's looking for, you know, cost is overrides everything else, including common sense, and that's what you can put in. That wouldn't work in this situation. Um, then we got two-stage. That's better. The two-stage, it has, 100% or 70%. It depends on the make and model. And that makes more sense because you don't need the full capacity all the time, just a few times. And the rest of the time you need a portion of that capacity. But then came along variable refrigerant flows, VRV systems or VRF systems, as they're sometimes called. That's that outdoor unit. The compressor in that outdoor unit isn't on or off per se. It's actually ramping up to meet your indoor condition. It's, you don't get that full load amperage draw right off the bat. It's a soft start inherently. Um, and it has a variable capacity. So in this case here, your heating load might be 36,000 if you customize it. That's in the coldest conditions in the winter. Maybe, in some places, the spring and fall is a lot different. I mean, your shoulder seasons, you don't need a fraction of that capacity. And that's where the variable refrigerant really makes difference. It just adapts to the load condition, and therefore it's extremely efficient. It's very quiet. Um, and these days, I think it's really your only choice because in that category of heat pumps, you can also add in or throw in cold climate heat pumps. They're variable refrigerant flow uh, pieces of equipment to start with, but they are designed to go to substantial sub-zero temperatures. A lot of benefits. Of course, there's a little bit of a balance. Your upfront cost is going to be different, a little higher, You got to measure that against your operating cost savings and comfort and all that kind of stuff. But generally speaking, from my experience, it's always, from a value point of view, it's always the best way to go.
Rob, one more question.
Okay.
It's a two-part question
All
because
right.
some of us don't know what SHGC means, but
I'm going to tell you.
what is SHGC? What do you normally assume?
Okay. Good question. I like that question because it's going to take us into our next part, which is, where did we leave off? Okay, if you don't mind, have a little bit of patience. We're going to get to that really quickly. I just want to start with where we get our input values, right? And this is important because sometimes they're on the drawings, right on the architectural drawings, right? Like in this case here, you can see them. The question is, when the architect did these drawings, was it coordinated with the energy advisor? Was it coordinated to meet the compliance requirements of the jurisdiction it's in? So on. And if the inputs that you see on the drawings are outdated, then it's going to be a problem, right? And it's often the case. They create the drawings, they assume the inputs, then they get an energy advisor, and the energy advisor says, "Nah, no, you're not going to meet the step code if with this assembly or that assembly, you're going to have to change it." And then they change it, but they don't update the drawings. That happens often. So if we keep in mind this one fact, that assembly details are always part of an energy advisor's report, whether it's a compliance report for new construction or a homeowner information sheet. An energy advisor that's on the project has the last say because that's the compliance piece. That's what the city is holding their hand out for, or the township or the region, right, the district. That's the promise that the builder makes to the authority having jurisdiction. This is what we're going to build. And so whatever's on the drawings or wherever else you get your assembly details from, it should align with the energy report, whatever was submitted for compliance. So just to that point, whenever assembly details are provided by more than a single source, it's critical to ensure that they line up with each other. And usually the energy advisors report, official report, the submitted report, not a report in progress, but the submitted report is the one that takes priority. Those are the details you want for RNU values. Okay, this is where we get to SHGC. SHGC is the solar heat gain coefficient of glass. That's basically, I'm not sure if I put the explanation in here or not. Let's just see. Here, yeah, we have it here. So we're going to skip ahead and go back. And it's a good question because it's the hardest value to get. A lot of times you get the R value of the windows or the U value of the windows, but not the solar heat gain coefficient. You cannot proceed. You cannot proceed with a load calculation without the solar heat gain coefficient. It's very, very critical. And it's very often the hardest thing to obtain. Sometimes you got to, pull teeth to get it, but it's necessary. And what it represents, just to say it one more time, solar heat gain coefficient. It's the fraction of solar radiation passing through a window and how well that window blocks the heat gain caused by the sun. It's measured between 0 and 1, so it's a percentage. The lower the number, the more heat gain is blocked. So if you imagine a clear window, like in a passive house, for example, the idea in a passive house is let all the heat in that we can. To make it clear, don't put much blocking on it. It's got a high solar heat gain coefficient because we want that free heat, right? Problem with that is passive houses tend to overheat in summer. Why? Because if you take a house that has a low solar heat gain number, that means that the heat coming in the house is blocked to some degree, enough that it makes a difference that it's not overheating the indoor space. And we'll see how much difference that makes in a moment. But first, I want to go back to here. So this is an example. The most common errors when it comes to windows is solar heat gain coefficient and overhangs. We'll talk about that in a bit. The other thing is infiltration. That is, it's surprising how that's not, how often that's inaccurate. And occupant load. Let's just have a look at the impact that these make. Now look at the numbers here. See this yellow, both in the heating and cooling, right? That obviously that's substantial, a large portion of the impact on both the heating load and the cooling load. So it matters you get that right. Infiltration, look at infiltration on the heating load here, right? Infiltration is, what is it, 26%. So naturally, you want to get that right. You don't want that 26% to turn into 50% or 5%. You want it to be accurate because it's so impactful. Internal gains. Other than glazing, look at what the largest portion of the thing that's contributing the largest portion of the heat gain is internal gains. Internal gains are 26%, right? So they matter. They really do matter. So back to solar heat gain coefficient. So in our sample house, we changed the baseline from SHGC, solar heat gain coefficient, from 0.3 to 0.5. Now remember, 0.3 blocks more solar gain, 0.5 lets more in. 0.3 is less clear, 0.5 is more clear. So here's the numbers once again, from 0.3 to 0.5. What do you think the difference is going to be? Is it 33%, 11%, 4%? Right. So is everybody in? I guess it is, eh?
Yep. So about a third say 33% increase, 44% are saying 11, and 21% are saying 4% increase.
Cool.
Big
Okay.
reveal.
I'm not going to tell you. No, I'm just kidding. Sorry. So 33%. 33% increase. Now let's just go back. Remember what we did. 0.3 to 0.5. That's all. So much. If you go to passive homes, they're like 0.6. An even bigger difference or even worse. One of the things that, like, this is the managing expectations part of it, but it's important. We come across this all the time. I have a view. I want to see clearly the view. And I don't want my windows to look like I'm looking through sunglasses. Okay, fair enough. But the fact is this, and the reason we pick 0.3, because that's kind of the threshold. You don't notice the coating on the windows at 0.3. Below 0.3, you start to notice. And even then, it's very acceptable to a lot of people to get even below that. But at 0.3, that's the threshold that we kind of start with as a default. Because these days with high performance homes, almost all the time we're dealing with homes where the cooling load is the dominant load. And people seem to have a lot less patience when they're overheated. Because in the winter they can always, put on the fireplace, put a sweater on, and so forth. So this is to answer that question. I don't want to be looking through sunglasses. You won't even notice the difference. When you're looking out your window, you're not going to know that this could have been clearer at 0.5. You won't notice. So and the window manufacturers, to them, it's no big deal. It's not like a huge upgrade cost or anything like that. They'll put on whatever you want. The critical part of the cost of windows from manufacturers and the suppliers is all about the framing and the hardware and everything else, right? Not the coating for the solar heat gain coefficient. So just making that slight difference in the input, the output increased by 33%. So it's substantial. The original cooling load, 16,175. go to a clear window at 0.5, and it goes up to 21,523. So it has a profound impact. And as I said, as we get better at building homes, they're more high performance than they ever were. They're less drafty. We have the ability to keep the heat in, which is designed for winter conditions, of course, because we're in Canada. And we're much better at keeping the heat in. Problem it happens in the summer. Um, the we still have the same internal gains. We still have the same lights and more equipment running, monitors and computers and whatnot, right? Um, we still have solar gain from the windows. We haven't changed that cooling part of it very much. So we still have substantial um, heat gains. Yet we don't have the same ability that we used to in older homes to dissipate that heat to outside, right? It's stuck inside more. So increasingly, cooling loads have become the more dominant loads, and it'll continue to do that, especially with the way the climate's changing. That's another additional um, feature on how it affects cooling loads.
Rob,
Mhm.
Angela asks, is the software sophisticated enough to account for the window shading difference winter to summer? So high SHGC might be okay if it only gets in the winter and shaded in the summer.
Oh, nice timing. That's what we're just going to talk about. Yeah, it makes difference. Makes big difference. Um, yeah, if you have clear windows, then you better put some overhangs on those things. Unless it's west facing where the overhangs, they don't do anything for you because the sun's low, right? It does your overhang is there for south exposures mostly, but the early morning, late day, west and east, the west especially because that's the lingering um, heat gain with the lowering sun until it disappears over the horizon, and that those overhangs aren't going to do much for you. But on the south facing or southwest and southeast, it makes a huge difference. So we took this house, and as we talked about before, you can see here, right, this on the south facing, like, they put pretty substantial overhangs on here. It's a good thing because it would have made a difference, and we'll see what that difference it makes in a second, right? So let's say they didn't put these big overhangs on here. What difference would it make? Here's the difference. We increased the cooling load by 22%, right? These are the overhangs. We just took them out. We had like many houses. There's no shortage of um, houses that are designed for so-called clean exterior looks, and so there's no overhangs, and those are a problem. If that was one of these buildings, and thank goodness this wasn't, it would have had an increased cooling load of 19,000, a 22% increase. And what we want to do when we have overhangs, first of all, we want to make sure we don't miss them, that we find them where they are, and we measure the height at the top of the window to the overhang and the depth of the overhang, how far it extends from the exterior building surface. We have to input those two numbers into each window. And as you can see, putting the overhangs on south-facing walls it's a huge benefit to do that. And then you can get away with more clear glass for that exposure. But if what we see here, if that was west facing, yeah, it will have some effect, but that sun will be low. And if you happen to have a bedroom like this right here, I think is a master, then that is going to be a lot of solar gain. You're going to have to use more energy to keep that cool so that when you go to bed, you're not going to be sweating. The other thing is infiltration. How drafty is the house? Infiltration is the amount of air passing through the building envelope that will affect energy performance. And it'll also, obviously if you got a drafty house, it's going to affect comfort. You can feel drafts, and nobody likes that. So it'll affect comfort, and it also will affect the structural integrity of the home. And what I mean by that is that when you have a leaky home, pressures, your house is always feeling some pressure, either pressure from inside or windy days, pressure from outside. It's never or rarely nicely equally balanced between inside and outside, between the top floors and bottom floors. There's always pressures going on. It's a dynamic situation when it comes to pressures. You got pressure, you got rainy days outside, and you got leaks in the house and building envelope, and it's pushing in moisture. Or from the other direction, because there's a lot of moisture inside house that we generate. In a house that's warm, it's pressurizing against the exterior surfaces, trying to get out. It finds leaks, it goes into those leaks, it hits the cold part of the building assembly, condenses, and now you got the potential for other problems, mold and rot and those kinds of things. So that's what I mean about the structural integrity. All that's to say, we don't want a drafty, leaky house. We want a nice, tight house. That we can control. And in this case here, because this is a step 5 home, we adjusted the ACH, which represents air changes per hour, measured at 50 pascals of pressure. Usually what we do is we pressurize depressurize the inside of the house. We do a blower door test, and we run a fan at a high enough speed that it's sucking out so much air that it equals 50 pascals, and then we see where the leaks are, if there are any, right? So that's the standard, the ACH at 50 pascals, air changes per hour at 50 pascals in this home. And this is in the code, by the way. This is how we have to measure it. This is what we should be seeing in our load calculations. In this case here, we adjusted it from 1.0, which is the requirement for step 5, to 2.5, which is the requirement for step 3. Before I go on, I just want to emphasize 2.5 is pretty good too. It's not bad. And what I want to demonstrate here is not that one is bad and one is good. Obviously, the tighter the better, but 2.5 is still considered pretty good. But it does make a difference. Let's see what the difference is. Okay, remember, probably getting used to these numbers here, 35,525 for heating, 16,175 for cooling. We changed it to 2.5, which remember is still good, but that still increased the heating load by 10%, more than 10%. We went, in this case here, to address the question we had before, would we go up to the next size or keep it at 3 tons? In this case here, now I'd be a little more cautious about keeping it at 3-ton system. We're now, I would be a lot more comfortable going up to a 3.5. Or depending on the manufacturer, they might not have half-ton increments. You might have to go up to 4 tons, but in that case, it'd have to be variable.
So, hey Rob, can you comment on, because Andy brought up a good comment earlier saying that like with existing homes, and it's important to plan for like the air tightness achieved instead of just the air tightness that's existing. And I think that that's fair, but it does come with some risk, especially with existing homes, and because of the high variability of you cannot predict what the infiltration rate is from house A that could be beside house B. So like measuring at the beginning is really important to understanding your baseline, but also like my experience has been, you need to be conservative if you're not doing like the envelope work and then getting an updated blower door test, to not predict what you're going to get, but what you actually get. Because like this infiltration exponentially is the biggest piece of the pie when it comes to existing homes. So do you want to just maybe expand on that a little bit? Because I agree with
Sure.
Andy's point, but it's like just be careful in terms of like measure, I guess is where I was going with that.
Yeah, well, that's a good question, and I think you answered it very well, Ryan, already. Let's see. of course, yeah, you need to do a blower door test, or somebody does, because you have no idea how drafty the house is, and chances are it's going to be very drafty. We see ACHs, for example, ACH at 50 pascals, their changes way over 10. It's like it's very, very leaky homes in a lot of cases. It isn't really until the last 10 years that we started to see tighter houses. So anything, you know, before 10 years is probably going to be really leaky, especially if it was built in the 80s, 90s, and so or before.
Yeah.
So that's the condition the house is in. If the homeowner just wants the heating system changed out, there no plans to do anything to the house, that's what you're going to work with, right? And so that's what you design to. But it's important to understand in a lot of cases, unless it's an emergency, homeowner is changing the heating cooling system as part of a bigger plan. And they are interrelated and interdependent. And if that's the case, then we have to set a ACH target, an infiltration target. We're going to do some weather stripping, we're going to do some sealing here and there, we're going to put in better window, whatever. Somebody's going to make an assumption. The target infiltration is going to be a guess. All right. It might be a good guess, but it's still a guess, right? Because you don't know for sure. Unlike a new house, you can manage that a lot better. If you're trying to save as much of the interior finish and everything and with the least amount of impact on the home, you have a limited amount of options, and the ability to reduce the infiltration and draftiness of the house is also limited. You can do a lot, but like Ryan said, you have to be very conservative. So if the EA report says, listen, if you do this, that, and the other thing, we'll go from a 10.5 air change to a 5.5. As a designer, I say 5.5. Okay, let's throw a couple numbers on there, make it 7.5, right? To build a little resilience in, and then verify it, right? Because if there was a target set, somebody's going to come back with that same blower door kit and see how we did, right? Usually by then it's too late. You've already installed the system, right? So as Ryan said, be very conservative with the guesstimate of what the air changes will be in an existing home, unless you're gutting it completely and exposing all the framing and the structure and effectively starting from scratch. Where were we? Infiltration. Okay, that's what we were just talking about. Excuse me. Okay, yeah. So we already saw what and this is in a new house, what the difference is, right? 10%. So it matters. It really matters, right? This is part again, managing the expectation, the go from a 2.5 to a 1.5, for example, might be all you need as long as the builder is confident that they'll be able to accomplish that, right? So you do need some pretty strict coordination. If it was a step 3 house, they have no choice. They have to hit that, right? But if they're doing step 3 and the builder's saying, listen, the last 5 houses I did, I hit 1.5 in every one or better. And I'm sure I can do it in this one. Okay, then you need that assurance. That's going to be the target and work at that. Also, mid-construction, you get to test it. That's when you get to fix whatever's wrong mid-construction before it's too late, before you cover it up, finish the house. Building assemblies, occupant load. So in this home, it's only got 2 bedrooms. So it has an occupant load technically of 3 people, 2 for the master, 1 for the other bedroom. It's 2 for the first bedroom, 1 for each additional bedroom. And so in this case, it's 3 people. That might not seem like a lot, but it does make a difference. Imagine a house with 4 bedrooms, 5 bedrooms. Imagine a house that has a a theater room in it. And you can see in the theater room, there's seating for 8, or where they got a huge dining table. And you can see there's seating for 16 there. Maybe they got big family and they're planning to have get-togethers and whatnot. These things need to be considered when doing your load calculations. The occupant load. Why? Because everybody gives off heat. We give off heat, we give off moisture, and it affects the heat gained from appliances. Like the number of people, there's an association, correlation between people and the amount of appliances that are used, cooking and computers, monitors, lights, and so on, right? That all contribute to the heat gain. So what we did here, just to demonstrate the difference it makes, we took out those 3 people. We only took 3 people out. In bigger house, that would have much more impact. 4 bedrooms, 5 bedrooms, much bigger impact, right? We took them out, and guess what happened? The heating load stayed the same, but the cooling load, the heat gain, went up 7%. And remember what I said, occupants are determined technically by code to meet the CSA standard. First bedroom is 2 occupants. Each additional bedroom is 1 additional occupant. Just like anything else, there's flexibility there, opportunities for customization. If it is apparent that there's going to be some, major peak load conditions, I want to entertain in the winter. I'll entertain in the summer. I got a pool out there. We've got lots of kids and grandkids, and there'll be, 20 of us in the house and cooking dinners and all that kind of stuff. Doors will be open, people running in and out, kids wet, bathing suits on and towels. That is a prime peak load condition. You got to say, okay, you got 2 choices. You can expect it to be, uncomfortably warm and humid in the house in that condition, or we can design the system to accommodate that intermittently when those occasions are occurring. Anyways, so that's about occupants. It makes a difference. Every one of these little things makes a difference. Okay, so we're at the case study home. And the interesting thing about this is because it demonstrates a couple things. It demonstrates what happens if the inputs aren't right. Something goes awry with the inputs. You end up with a load calculation that's not accurate, right? This is about load calculations, doing load calculations, but it's also a nice segue into the next section that we're going to do in November, which is about how to use the load calculation to design your system. And this is a great case study for that as well. So this house is actually just over 2,200 square feet. It's just recently built by the homeowner. Now the homeowner is a commercial architect, so and so is his wife. And so they had, better understanding than most of building processes. And so they didn't want to go to expense of hiring a builder. They decided to manage the place themselves. It's in the lower mainland in a small community, climate zone 4, built to step code 4. The energy modeling, the load calculations, the whole system design Ecolite did, was done in-house. And this is what we came up with for just the loads, among a whole bunch of other things. Heating load, 18,870, and the cooling load, 39,000, more than double, right? There's a lot of reasons for that. And we'll discover some of the reasons for that as we go. Okay, so keep that in mind. That's what we came up with. So the architect, they're the builder, the homeowner, not the builder, he was all these things. But they didn't get the process that well. And, they hired a local, actually lives down the street, HVAC contractors. By the way, good contractor. But that good contractor didn't know the few things. He knew we were involved, but he thought that we were just helping him out, give him some guidance, some general ideas about location of ducting and that kind of stuff, but didn't think that we did anything detailed on it. And one of the reasons he thought that is because he wasn't given given the load calculations, among other things. It wasn't coordinated. Next thing you know, the house is built really quickly, and boom, we find out, holy shit, we got to go out and do a site review, right? And it is getting close to occupancy, and so there's finished walls everywhere. And we discover a few things. We discover different equipment. That's the first red flag. Different size ducting. Second red flag. What the hell? And so we talk to the homeowner and say, I'm not sure what went wrong here, but our design was very explicit, very detailed about equipment selection, sizing, load calculations, heat pump performance curves, balance points. Everything was in there. Resistance checks on the ducting, everything. And we coordinated this with you. We've got like a dozen versions of this, to make the aesthetic work for you. But now we end up with this one, what's happened. Well, that contractor, the HVAC contractor, didn't realize that we had done a load calculations. And as I said, he thought it was a guideline that we're just helping the guy out. And so he sent it to a third party and got his own load calculations done. And look at the difference. Same house, two different load calculations. Calculations A, that was us, 18,000, almost 19,000 BTUs heating load. It went up to 28,000 BTUs with their calculations. Our cooling load, as you saw, was shockingly 39,000 and change. Their cooling load, 28,000. Obviously, this is an issue. We have to figure this out, right? So we did. We did a reconciliation of the differences, the significant differences, and did a very detailed line by line review, because there's a lot at stake here. I mean, they're ready to move in, and they're wondering what do I do now? Am I going to be uncomfortable? Do I put in bigger equipment? Or if we do that, we're going to have to rip out some ducting because it's not sized, all that kind of stuff. It's a major, major issue. And so it is, and it was therefore exceptionally important to do a very thorough level of diligence on reviewing these load calculations, which we did. And for the most part, it was, the inputs agreed with each other with a few exceptions, and here they are. The indoor-outdoor design conditions for the B set, remember that's the one they didn't reflect the client's expectations for indoor comfort and climate resiliency. That's the first thing. The first thing you ask the client is what is comfortable, among other things. I mean, you also want to know their budget and everything else, right? There's a lot of things that go on that we call discovery and coordination. But in any case, and here, we had done a lot of back and forthing with the homeowner, and we, came to conclusions about what they wanted. It was their expressed desire to have certain indoor conditions, and they wanted resiliency, because in that community, especially when they started building a house, it was crazy hot. I had gone over the seasonal averages by quite a lot for an extended period of time. And him being an architect, he was very well aware of, the conditions that climate change is causing. So he wanted the resiliency. And so this is what we designed for it. Calculations A, 19 outside for heating. This is in Fahrenheit, sorry, it's all in Fahrenheit. 72 inside for heating, 91 outside for cooling, 74 inside for cooling. They did is the same for heating, but they went to the BC cooling, 82.4. 82.4, I mean, yes, just this past summer, we blew past that number many times for extended period of times. And this is not an outlier year, right? But anyways, so that's what they did. And they did the standard, the ASHRAE, remember somebody referred to that, 70 indoor heating, 75 indoor for cooling. There's no way, it's very rare that we meet people that are happy with 75 as a design condition for their indoor temperature. Okay, so that is discrepancy number one between our load calculations and theirs, A and B, okay? Second, there's a large skylight in this house. Skylights, they make a big difference. You can't miss those things because it'll mess things up if you do. You can see there's a huge skylight. It's massive, right? Obviously, we got it on ours, but they didn't. There was no skylight in their load calculations. Of course, that's going to make a difference, right? Here's a couple of other things. Double glazed windows were input for the B set. Meanwhile, there's triple glazed windows that are actually going into the house. That makes a huge difference on the heating, right? Among other things. And one of the reasons they wanted to triple was because they wanted, of course, good performance, low carbon footprint and all that. But they also wanted to have a quiet indoor environment. That was one of the reasons they went for triple pane. Number 4.
Rob?
Yep.
Edwin asks, do skylights typically have the same range you discussed of solar heat gain coefficient?
Yeah. Skylights are a particular case. Skylights are usually there to provide light, not a view, right? Unless you're thinking of a view of the sky or the clouds. Because of that, you can go down to the lowest solar heat gain you can get. You can make it look like sunglasses up there. It doesn't matter. It's just bringing light in. The light is still there. You're not blocking out light, just blocking out the part of the waveform that creates heat. And so with skylights, it's important to negotiate or coordinate a very, very low solar, the least they can get away with, right? That the manufacturer's willing to supply. That makes a big difference. But otherwise, yeah, it's a U value for the glass in terms of a heat loss and heat gain, or sorry, the heat loss. The better it is, just like a window, at resisting heat loss, the better it is for the house, especially something right overhead like that, right? The windows were modeled with shading from interior blinds in the B set. Problem there. One problem is there's no blinds. There's no intention of putting blinds. There's no blinds. It's very architecturally driven, aesthetically driven house. 2 architects. Don't forget. No blinds. Interior blinds. Even if you did have interior blinds, the amount of heat gain that is blocked from those interior blinds is minimal. It's insignificant because once that heat is past the window and into your living space, it's in your house. It's in your room. The difference is instead of creating a hot spot on the floor when the sun's shining in, that delivers heat to the room that you don't want. Now that heat is being absorbed by a vertical set of blinds, and now you have a vertical from ceiling to floor almost, or whatever that size the blind is, radiating heat outbound into the room. Either way, it has even if there's going to be blinds and they promise that, oh, I swear I'm going to close those blinds, I'm never going to open them, which you would be a fool to believe. Even if they did do that, it would have extremely minimal, inconsequential impact on the cooling load. But it's in here, and it's a substantial amount of shading. 50% is what they put in for this, right? Obviously, that's going to make a massive difference. And this is a house that's on the side of a mountain that's looking west toward the ocean in the distance. There's, you know, the outline of Vancouver Island. That sun just lingers and lingers and lingers, you know. It's got incredible views. So, you know, that's another reason they wouldn't have blinds, and part of the reason value of the house and having those windows is for the view. So we have, again, let's look at this, 18,000 BTU to 28,000 BTU. Obviously not going to work. 39,000 BTU down to 29,000 BTU, 28,000 BTU is obviously not going to work. They're going to have to change it out. They're going to have to change equipment and the ducting. There's no way around that. Just to encapsulate the issues that we discovered. One was the indoor-outdoor design condition. It didn't meet the client's expectations, no resilience, and so on. Large skylight missed. Double glazed windows were input instead of triple glazed. And windows were modeled with window shading from interior blinds when there's no blinds, and even if they were, to make very little difference anyways. There's a considerable impact of this. Imagine, I mean, not only is it an issue for the HVAC contractor, God bless them, they're usually very good. We know them. They're good contractors, and they're, you know, conscientious. So they're probably going to eat some of those costs. I don't know how that's going to work out. But obviously, it's not good for anybody how this turned out. What is good is that we got a chance to do our quality assurance, and we discovered this before it was, you know, far too late. And so, given all that, let's contemplate this question. What was the most impactful error regarding load calculations for this house? What do you think? Which one of these? Incorrect indoor-outdoor design conditions, missed skylight, double instead of triple pane windows, interior blinds for shading, or none of the above?
This is interesting.
Okay.
I really want to know the one.
So the majority picked the incorrect indoor-outdoor design conditions. Good choice. Missed skylight, yeah, good choice. And just as many picked a double instead of triple pane windows. 12% picked interior blinds, and only 2%, one person picked none of the above. Well, congratulations to that one person. It's none of the above, right? And the reason I say this is because one of the things when you're doing load calculations, you can't do it in a vacuum. You don't want that HVAC contractor sending off the plans to the supplier and saying, listen, and you know, do the load calculations, give me the loss leader load calculations, I'll buy my stuff from you. That never goes well. You have to have some skin in the game. You got to be engaged with the project. You have to ask the questions. You have to coordinate. In this case here, that coordination didn't happen. If the coordination had happened, if proper coordination had been performed throughout the construction phase, none of the above errors would have occurred. None of them. Now, of course, each one of those, as you can see, has major impact, right? And that is an example of what happens when, you know, you just get one thing wrong. But imagine when you amplify that by more than one thing, that has massive potential massive project impact, schedule, cost, and so on, right? But ultimately, I think just like a design, you're part of a team, right? And you need to coordinate with the other members of that team and make sure that coordination starts at the beginning of the project and continues throughout the project. And if that had happened, none of those mistakes would have occurred. So that was the point of the none of the above. I know it was kind of a trick, cheeky. Oh, sorry about that, but I just wanted to emphasize. I think we all understand what 1, 2, 3, and 4 will do, but I just thought it was important to emphasize the incredible impact that the proper coordination or lack of it would have on the project.
Rob, I just want to say we love cheeky around here, so bring it.
Anyways, talking about cheeky, we're at our everybody's favorite slide. As to thank you, and if there's any more questions or comments, I'd be happy to talk about them.
Hey, and there's a few final slides from us too, so remember not to sign off just yet and to help us do your final poll to tell us what you loved, what could have been better, and what you want next.
If no one asked a question, Andy's hitting all the points. And it might be a good tease for the next one, Rob. He said, and don't forget about HVAC commissioning. And I know we're going to talk about equipment selection.
Yeah, it's a different, yeah, you know, you're absolutely right. I mean, we're talking about load calculations, and load calculations, of course, is one part of the journey, you know, that as HVAC contractors or designers that the journey that we're all on, right? For the process of building a house. And as far as commissioning goes, there's a whole set of other things. And I think we're going to touch on that quite a bit in our next session, right? The impact of load calculations on equipment selection, choosing equipment, how to choose equipment. Is a big thing. And then, of course, you know, you can't just choose equipment, you have to actually install it, you know, so the importance of design, coordinating for that. You can't just design a system, you have to do some quality assurance, you know, you have to make sure that system was installed to meet the design intent. It doesn't have to be precise, it just has to meet the design intent, you know, keep everybody happy. Part of that is not just good installation practices, and we'll talk about that too in our next session. It's also critical. It's important. In fact, I think it's irresponsible not to do thorough, proper commissioning. You can't just install a system, turn on a thermostat, feel the air with your hand over a register. Oh yeah, that's on, it's running. Okay, pack up the tools, clean up and go. You have to check stuff. You have to, you know, the manufacturer wants you to check stuff, otherwise it voids the warranty. You have to see, did it meet our targets or not? Can we rebalance it a little bit? To do that, are the controls, especially if there's zones or other things going on, responding adequately to calls for heat, calls for cooling, and that kind of stuff. You know, there's a lot to commissioning, and we could do a whole session just on commissioning, but it's pretty important to your point. Yeah.
Rob, I got two questions. One is, do you have any further slides after this one related to CEA stuff? And if you don't, I'm going to share my screen shortly.
I do.
Okay, cool.
Yeah.
And then two, Brooklyn asks, can calculations be completed accurately without a site visit? For example, if a contractor provides all the relevant building details to the energy advisor remotely, how reliable would those calculations be compared to an in-person assessment?
Well, in new construction, we do have to accept there's a certain level of professional integrity is going to be applied, but there is a requirement for energy advisors to do a mid-construction blower door test, and that's usually when, and at the end they have to do a as-built, and their certification is on the line, right? The other thing too is, I guess it's not the same for everybody, but you know, when we were HVAC contractors for years, I don't forget, I know I spent half my life with the tool belt on. So you get comfortable in the environment of construction site. And you should be, if possible, be able to go to the house before they cover it up with drywall and everything else and check. They said they're going to spray foam these walls. Is there spray foam? You know, the tags on the windows, you know, the windows delivered say a U value of this and a solar heat gain of that. Is that what we agreed upon, you know, and that kind of stuff. As an HVAC contractor, because I'm the one as a contractor or a designer is going to get the call if it's not heating or cooling, right? Not the EA, right? They don't even know what an EA is by the time they're living there. Um, it's either the builder or the who's going to call you, or it's the homeowner who's going to call you, and you have to deal with it. So it's in your interest to make sure that what was promised to be built was delivered. And if there were changes, and changes happen, that they are manageable, that they're known, you're not surprised, and they're coordinated. Does it affect my design? You know, what do we have to do to mitigate those changes, if anything, right? So the energy advisor has a responsibility to maintain their certification with NRCan, to provide as-built that reflect the actual building. And if then they get audited. So if they're incorrect, their certification may be revoked, or they might get in some trouble. As HVAC contractor, it's good to check and say, hey, you said you're going to put spray foam in those walls there, and there's just bad insulation. That's not going to work. We got to do something about that, right? Or maybe there was going to be bad insulation. Now there's spray foam. Oh, good. Okay. It might not be a problem. There's no point creating drama where there's no need for it. But it's good to know. That's what I call simply coordination. Coordinate. Always know what's going on. Be proactive, not reactive. You know, be engaged, care about the project. If everybody's doing that, then it's going to create the best outcome for everybody.
We have another question. Meredith Hamstead asks, what do we do if there's no set of plans for a retrofit context? Is there a verified software that allows for a scan with phone to F280 output?
No. There was a
Sure.
program. What was that called?
Yes.
Cool Calc.
Meredith's being cheeky. I like it, Meredith. Yes, there is a new software tool from
Oh, that's the measuring tool. Yeah. That's right. Yeah.
But
Yeah.
again, you know, it's back to that old sort of like adage. You need to make sure that when you're scanning and using a tool that can give you some measurements where architectural plans don't exist, that the inputs are accurate. And so, you know, the garbage in, garbage out kind of cliche, you know, is one of the things that we want to emphasize. Like the more assumptions
Yeah.
you have, or the more incorrect values you have, your risk exposure increases exponentially. So
Yeah.
it doesn't matter about the tool, it's about the person using the tool and making sure that they're qualified. So yes, it's Stride. I knew it would come to me. Yeah, I mean, if people haven't checked it out, it's good to sort of like read up. It's a new tool that's come into play to help facilitate gathering inputs and gathering measurements in terms of window wall ratios and geometry and that kind of thing, where architectural plans don't exist. So encourage to have a look.
Yeah. And you know, um, we're still quite a long way off from being able to hand it over to AI to do all the work. You know, it's luckily for the time being, anyways, it still needs humans. Maybe bots will be doing it down the road, but hopefully I won't be around for that. But yeah, for now, that is just a tool, right? That's all it is, just a tool. It might be a good tool, but it's just a tool. Any more questions? Should I go to the next slide, the CEA slides?
Sure, please.
Okay, here we go.
Yeah, just a reminder, we're going to do a final feedback poll. And just before that, I just have 3 more slides to get through. I'd like to thank our sponsors and
Oh,
partners.
Is this the one you want up
Yeah,
now?
this is beautiful. Thank you.
Okay.
That was just a reminder to let everybody know, including myself, that we still have that one last thing to do.
Yeah,
But
that poll. Yeah, that's going to be whether or not I get paid.
well, that's true. Yes. Yeah, that is there's a bonus here depending on the feedback. So thank you, Rob Pope and Ryan Coleman from Ecoliten. Really enlightening presentation today. Thank you for that information, and really looking forward to the next part in the series on November 20th. This has been brought to you by Canadian Home Builders Association, Northern BC, Regional District of Central Kootenay, Regional District of Kootenay Boundary, with primarily funded from BC Hydro. Next slide, please. So I mentioned those upcoming events in the chat and just now. So we have the F280-12 calculation, how to interpret them. And we're doing a bit of a roadshow around the province from plans to performance. Those are in-person webinars looking at integrated design process, or that coordination as Rob calls it, and integrating HVAC as well. Next slide, please. Just wanted to give a little plug for the Home Performance Contractors Network. You can join them. There's training subsidies that are available, and membership is free. There's the email there, info@homeperformance.ca, for more information. I know some of you on the call are part of that network already. They can help you to get some of the rebates that are available for retrofits. There's training available to make you a qualified contractor on various streams. Energy Advisor is one of the new ones. Windows and doors, I believe. There's a bunch of different ones. Please go check them out. And maybe one more. There it is. So the residential air to air heat pump specialist micro credential is available. Best practices and design considerations to ensure quality heat pump system installations that meet homeowners' expectations and provide heating and cooling during extreme weather events. This is a micro credential that's offered, I think it's a partnership between HBSC, TECA, and BCIT. And there's the link. Again, we'll be sending out these slides. And now I'm just going to launch that final poll that I promised. Thanks, everybody, for being here, and looking forward to seeing you again very soon.
All right. Thanks, K10. I'm going to jump off. Rob, awesome. See you again, Amanda.
Thanks,
Thanks,
Ryan.
Ryan.
Bye.